Hey there, welcome back to Short Take 331. Today we're going to talk about calculating roots, the bisection algorithm. So this is our first episode on root finding. We're going to have multiple parts on this. And actually root finding, I like to say it's a misnomer. What we're really doing is root calculating. We're not going to be designing an algorithm that goes and finds all possible roots, but rather we're going to focus on a root that we want to calculate, and then we're going to try to refine the knowledge of that root. But let's start from the beginning. So what is a root? A root is a solution to an equation of this form. So we have some kind of function, p of x, equal to 0, and so we want to find what values of x, or we want to find specifically a value of x that solves this problem. And in the simplest possible cases, p of x could be a quadratic polynomial where we have a formula, the quadratic formula. There's also formulas for the cubic polynomial and for quartic polynomials, so polynomials of degrees then 2, 3, and 4. And by the way, generally a polynomial could be of any degree, right? It could be a sum from k equals 0 to n of some coefficient a sub k, x to the k. And so this degree n, if a sub n is non-zero, then that would be the degree. Otherwise, in this expression, the degree could be less or equal to n. But in general, this n could be anywhere between 0 and infinity, as some fixed number. So we have formulas, like I said, for 2, 3, and 4, but n could be 5, 6, or 7, some other high-order polynomial, and so then we'll be in trouble. And the reason we'll be in trouble is reflected in one of the two theorems I wanted to emphasize today, and that is the Abel-Ruffini theorem, which tells us about the impossibility of solving this kind of equation, p of x equals 0, for the roots. So a polynomial root, basically, a root of a polynomial, or the root of an algebraic equation, if you want, for degree 5 or higher, in terms of radicals. And here, in terms of radicals, means with operations that involve addition, subtraction, multiplication, division, and taking nth roots of the coefficients in your polynomial. And so that basically tells us there's not going to be a simple formula. There's not going to be a formula with square root or cubic root or something like that, and addition, subtraction, and division. And there's not going to be anything like that for degree 5 or higher in this polynomial. So if n is 5 or higher, and again, assuming a sub n is non-zero, then we'll be in trouble. But on the other hand, we do have the fundamental theorem of algebra that tells us that all the roots for polynomials are in the complex plane. And so no matter the polynomial, so all the solutions for all the algebraic equations are in the complex plane. And so we can be safe that the roots exist and they're out there, but we just need to find them. And if we have a rough idea of where they are, we can go in and try to refine that knowledge and calculate them. But of course, p of x, our function, doesn't have to be a polynomial. It could be much more complicated. It could be some exponential like this minus some trigonometric function, or multiplying. It could be some complicated mess. It could be the result of a complicated integral whose form we don't really know, and we're evaluating numerically. And so we need somehow numerical methods to approach the problem of calculating roots. And so the first method that we're going to see is bisection. And I like to say this is a modern approach to bisection, because one of the things that one should always do when finding roots is to plot the function. This historically was not so easy. I think in the early times of computers, where the graphics side was not very powerful, then that might have been complicated. But now we have really powerful graphics and really powerful computers, and so it's not too hard to at least have a rough idea of what our function looks like. This curve may not necessarily be continuous. You may be able to only throw some points on a graph, but you have a rough idea of where the roots are. And what we need for this bisection algorithm to work is to bracket the root that we want. So suppose in this case that we want to focus on this solution, p of x equal to 0, around this point, and we don't know exactly what it is. We don't have a formula or anything, but we have a rough idea of what it is so that we can bracket it. We can define an interval a, b, where we are sure that the root is there somewhere. And so we know that the root is between a and b, and we check that p of a, so the value of the function at this left-hand side or leftmost side of the interval, is of a different sign than p at b. So of course here p at a is positive and p at b is negative, but you could have the opposite situation, right? Negative and positive for this other root over here. That's okay. The algorithm will work either way, but let's focus on this one just to fix ideas. And then we'll talk about more complicated cases. So the first step, once we have this bracket well defined and we've checked that p of a and p of b have different signs, then we know that if our function is nice and continuous and there's no weird discontinuity, which is of course something that you have to check, somehow your context has to tell you that you don't expect any discontinuities, otherwise all this would fail. But if we are sure that the function is continuous, then it has to take on all the values between p of a and p of b in a continuous fashion, because we know there are theorems from calculus that guarantee that has to be the case if our function is continuous. So that being established, then we will estimate the root, the first estimate of our root, as the average between a and b. So somewhere in the middle of this interval, there's a root. Now, of course, here the root is a little bit to the left, but this is our first estimate, if you want. And at least on the scale of things here between a and b, it doesn't look so bad. Now, what happens next? Well, to proceed with this algorithm, we're going to calculate the function at a, the function at the middle point x of r, this first estimate of the root, and the function at b, at the right-hand side of the interval. Now, in a way, we already had p and a and p of b, so we may not need to recalculate that, but we will need to calculate the function at this point, at this middle point x of r. So it's already calculated in step 2, so we saved it. And so we have p of a, p of xr, and p of b. So what do we do next with this information? Well, if p of a and p of x of r have the same sign, we're going to shift that left side of the interval from a to xr. So over here, let's see. P at a and p at xr don't have the same sign, actually. So this is going to stay where it is. Now we evaluate the next statement. If p of b and p of xr have the same sign, we're going to shift b to xr. So we go back to the plot here and we look. We see, yes, p at b and p at xr here, they're both negative. So we're going to shift this out of the interval all the way to here. So we can discard this whole section between x of r and b, because we know that the root is not there. So if the function has the same sign of b and the same sign of x of r, then we're going to discard that whole chunk of the interval, this whole chunk, this right side of the interval. And we're going to focus on what happens between a and x of r. And so with that information, now we return to step 2 with the updated values of a or b. So usually you're going to update one or the other, because the function will take different signs on each side. And so here we updated b. And so what do we do next? Well, we calculate the middle point. Here it will be somewhere over here. And so what happens? We're going to shift a, and so on and so forth. And you see we're going to end up bracketing the root in smaller and smaller intervals. And that's the idea of bisection. Basically, you stay within this loop where you go from step 2 to 3 on and on and on until you have refined your root as much as you want. So when do you stop? Well, after n steps, that size of the bracket, which was between a and b, will have gone down by a factor of 2 to the n. So this converges very quickly. This converges exponentially. So if your original size is b minus a, then after n steps, the size of the interval will be b minus a divided by 2 to the n. So you see after the first step, you saw over here, after the first step, we discarded this chunk and the interval got reduced by a factor of 2. So now we're only focusing on this half. After the second step, this a is going to be shifted to the middle here, and we're going to be now 1/4 of the original interval, and so on and so forth. And so what that tells us is that after n steps, again, we'll have b minus a divided by 2 to the n. Now, if we want to bound the root, if we want bounds on the root of size delta, so an error of size delta over 2, then what we want is to target the size of the interval that is of size delta. And so b minus a divided by 2 to the n, for some high enough n, is going to match that delta or go below that delta. And so if you solve then for n, you put 2 to the n on the side of the equation, you divide by delta, and you take the logarithm base 2 on both sides, and then so you get that n has to be the log base 2 of b minus a divided by delta. So this is going to be presumably some large number, but you take the logarithm, it's going to be a much smaller number, and that's the number of steps that you have to execute for this algorithm. So at least that number of steps. So usually this is not going to be some this logarithm is not going to give you some nice round integer. That's okay. You can go one more step and you can be absolutely sure that you'll be within this bound of size delta, and you'll have a precise result. When this algorithm works, it's actually very, very powerful and very quick. Now, remember, we assumed that the function was continuous and so on, but there's also other caveats. And one that is especially weird and that we all wonder about is what happens if your function looks like this. It just touches the x-axis and then it goes back up. So we don't have a sign on both sides that is different. And so it looks like we can't even start the algorithm. So p of x has the same sign, positive sign here, left and right, like sort of like a parabola, or it could be something of a higher order. And so how do we calculate in this case? What do we do? Well, there are different algorithms, different things you can do. One thing you can come up with that you can sort of think on the spot right away is say, well, okay, so if my function happens to be also not just continuous, but also differentiable, or that is pretty smooth, like you sort of see here, then you could imagine doing a tangent line over here. So in other words, you go and see, well, the root is here. I can see that it's here. So it's between some A and some B over here. So you can do a tangent line on the left and a tangent line on the right. And then you can say, well, I'm going to approximate the root as being between this point where the tangent line crosses the x-axis and this point where the other tangent line crosses the x-axis. And so you make that your new interval and you proceed to do the same thing. And as long as your tangent lines don't cross each other to the other side of the interval, then you have an estimate for your root. And so that's one thing, one algorithm you can imagine developing. I'm not going to talk about that algorithm further here, but you can think about it. Or if you feel that doesn't work, that may run into trouble, you can think about how to cure the problem that that kind of algorithm may have. Because of course over here the tangent to the curve will have zero slope, and so it may take you in some weird directions when you try to extrapolate to the x-axis. If you have zero slope, then the extrapolation to the x-axis will take you to infinity. So you have to be careful about that and think how you might want to stop that algorithm from diverging. So that's about it. That's all I wanted to cover for today. As always, if you enjoyed this video, please consider liking and subscribing to the channel. And as always, if you are looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. And that's all I have for you, and I'll see you next time.